Okay guys, so today we are going to look at limits involving infinity. So we're going to look at either when x is approaching infinity or the value of your limit equals infinity. So far in class we've only talked about either x approaching a value, so x is approaching 2, either from the right or the left, and then your answer is either does not exist or a number, 18, 0, -1. And today we're going to look at what happens, or what does it mean graphically, when both those things, either one of them, x is approaching infinity, or your value of your limit is equal to infinity. So before we can start talking about that, I want to talk about how big infinity actually is, okay, and different sizes of infinity. So picture a number line in your head for a second, and that number line is the length of infinity, okay? So your infinity is different than my infinity, right? We just know it's massive. Now if you take that number line, and now that number line becomes the side of a square, we would say that that area of our square, which I know in my picture looks more like a rectangle, but that area is infinity squared, for instance, okay? But that, excuse me, I just lost my voice for a second. Infinity squared is really just infinity, right? Like we don't deal with infinity squared ever. So when we deal with different magnitudes of infinity, it's because like a squared infinity is bigger than not squared infinity. Okay, just like a squared 2 is bigger than a 2 that's not squared. Now they're both so big that it's just a conceptual idea, but there are different sizes of infinity, and it's important to keep those things in your head as we are talking about infinity. Okay, so go ahead, pause the video, and write some notes to yourself, like about different sizes of infinity here, okay? Once you do that, go ahead and answer this question. What is the difference between x approaching infinity and the value of your limit being infinity? Okay, so what I'm asking is, what's the difference between like the limit as x approaches infinity of f of x equaling some number, and then for this one, like what's the limit as x approaches c of some function equaling infinity? Like how will those two things appear different, especially in a graph? Okay, like what's going to be different in a picture of those functions? So pause the video again for a second and record some of those notes to yourself right about here. And then when you're done with that, go ahead and in your own words describe what a horizontal asymptote is. Okay? Okay, so once you've done that, let's go ahead and look at the formal definition of a horizontal asymptote. So hopefully we know that a horizontal asymptote is a horizontal line that your graph can never cross. Okay, now that's not necessarily a mathematical definition of it. So we say that for the definition of a horizontal asymptote, the line y equals b, okay, keep in mind that we know that this is a horizontal line because like it would go through your y-axis at b, okay? So the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either of the following are true. The limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. Okay, so let's think about this for a second. So we know a horizontal asymptote is a horizontal line that our graph can approach but never cross. Okay, just like a vertical asymptote, we can approach it but we can never cross it. So let's think about what's happening here in this definition then. Okay, and I'm just going to draw it up here for the sake of space. You should draw it where you have space. We have a graph. Okay, and our b value, let me just do it in different color because I'm sick of blue and purple, is right here. Okay, so we have a curve that's approaching that value of b. Now, for every value of x, whether x is 2 or, 1,000, this obviously is drawn to scale. Haha. Okay, so for every value of x, as x is going towards infinity, no matter how big x is getting, our function value is going to get stuck at b. We can never pass b. And that's what this is saying. No matter how big of an x you have, you're never going to pass b, or the opposite. Okay, no matter how small of an x you have, no matter how close to negative infinity you're getting, how small you're getting, you're never going to pass b either. Okay, so that's the idea of these two values, these two definitions. So let's use both of these definitions to identify the horizontal asymptote of this function here. And this is where math rules get a little wonky. So let's look at this problem together. So we need to figure out the limit. It's asking us to identify the horizontal asymptotes. So based on our definition, we need to calculate the limit as x approaches infinity of x over the square root of x squared plus 1. And we also need to look at the limit as x approaches negative infinity of x over the square root of x squared plus 1. Okay, now here's what we're going to do, and we're going to look at these two problems separately. So just like before, we're going to substitute in the value of whatever x is approaching into our function. So this is going to get me to infinity over the square root of infinity squared plus 1. Okay, and right now that means nothing to us at all. That means nothing. But remember, a limit is an approximation of what's happening. We're predicting what's going to happen. So we don't really need to worry about this 1 right here. Okay, so think about it like this. If you had $1 billion and you lost $1, would it matter? Like, probably not, because you're so rich, $1 doesn't make a difference. So I'm just going to get rid of that 1. Whoa. Cancel. Am I still recording? Okay. So I'm just going to get rid of that 1, because it does not matter. It's not going to make any sort of difference. Right? If you have $1 billion, you lose 1, who cares? Even if you had like $1,000 and you lost $1, it wouldn't be a big of a deal. Okay? So once I do that, I'm left with infinity over the square root of infinity squared. Okay, now the square root of 4 squared is 4, so the square root of infinity squared is just infinity. So that's infinity over infinity, which is 1. Okay, so that tells me then that I have a horizontal asymptote at the value y equals 1. Okay, so I'm just plugging in infinity and then figuring out where can I reduce it to until I get a value of my answer. Okay, and we're going to do the same thing on this problem over here to deal with negative infinity. So I'm going to plug in negative infinity over the square root of negative infinity squared plus 1. And again, if you owe the bank $1 million, paying them $1 means nothing, right? You're still going to owe them a whole bunch of money. So that 1 is irrelevant in this problem. So then I'm at negative infinity over the square root of negative infinity squared, which is just infinity squared, which is negative infinity over infinity, which, surprise, surprise, is negative 1. So that means we have another horizontal asymptote at y equals negative 1. So in this situation, we have 2 horizontal asymptotes. So what I would encourage you to do, sorry, my dog just sneezed. What I would encourage you to do is graph this function and verify those asymptotes exist graphically. When you're done with that, continue on with your notes. So in your own words, describe a vertical asymptote. So pause the video to do that. Okay. So then, now that you've described it, let's think about it, and you should actually have this answer based on your rational expression, your graphing rational function notes that we did last class. So a vertical asymptote occurs when you have a rational expression in which the denominator is not a factor of the numerator. Okay, so you have a vertical asymptote when you have a rational expression in which the denominator is not a function of the numerator. Okay, so let's look at then the formal definition of a vertical asymptote. Notice in this definition it starts with x equaling a, because vertical asymptotes go through the x-axis. So like if this was a, it would go through that value. Okay, so the line x equals a is a vertical asymptote of the graph of a function f of x if either the limit as x approaches that value from one side, so let's just start with the limit as x approaches a from the left of our function is going to equal plus or minus infinity, or if it comes from the other side, not of, erase that, or the limit as x approaches a from the right of the function is going to also equal plus or minus infinity. Okay, now if you look at my little picture for a second, it makes sense. So if that's my function, it's coming down, or it's going up like that. As I'm approaching a from the left side, the value of my y value is going towards infinity. As I'm approaching it from the right side, my y value is going towards negative infinity. It's going downwards. Okay, that's what it means. So you already know, in order to identify a vertical asymptote, they occur when your denominator equals 0. Okay, so in this case, x squared cannot equal 0, right? Because that would make our function undefined. So where that occurs causes a vertical asymptote. So that would mean this function has a vertical asymptote at 0. Okay, and you can graph it to figure that out as well. And if we went to the other one, example 3, x minus 2 cannot equal 0, so we have a vertical asymptote at x equals 2. Okay, now, this question in particular is not asking you to graph. It's not asking you to solve for the limit. But if it was, you would need to think about graphing it like we did in class together last time I saw you. Please make sure if you have any questions, you're asking them, and I will see you in class next week.